Hello, this is Jeffrey Fox again, and we finally come to our discussion of a core collaborative filtering algorithm, which is the user-based nearest neighbor method. So in user-based collaborative filtering, we're choosing one of the three key methods. They are user-based, where you take a given user, find similar users to that user, and look at the likes and dislikes of the other users to find the interest of the current user. In item-based, you use the same data, the rankings, but instead of finding users near your current user, you find items near the current item chosen by the user. And the other one, which we actually saw illustrated by Pandora, content-based, we use a totally different data. We don't use the rankings, we use the properties of the items. Um, if somebody bought a red balloon, maybe they'd like to buy a green balloon, and things like that. Or if they bought a red balloon, maybe they'd like to buy a red jacket. Who knows? You'd have to look at some other features to decide what to recommend. Anyway, let's come to this user-based method, which essentially has this basic theory. It's not, of course, a real theory like Newton's law, but it's the assumption of the method that people who had similar tastes in the past will have similar tastes in the future, and users who have similar tastes to a given user that on a certain set of items, that similarity is quite likely to continue. The input is this matrix, which has, say, rows are users and columns are items, and there's a ranking or just a check mark saying user purchased item. And the output is a numerical prediction indicating to what degree a current user will like or dislike each item. And it will look at all items in this way and return the top ranked item for the user. It's difficult as you have to evaluate all the item ratings for each user. And in the alternative item base, you can find out this, make this prediction independently of the user, which items are near a given item. And so the item based is less computationally intense, especially for real-time applications. So let's sort of give this example coming from this nice recommender book. Several of these slides, of course, come from this book. So you have this database, or actually, it's not going to be probably information. It's a matrix. You have a new user called Alice, and she has is Alice, and she has ranked items 1 through 4, and we want to make a decision about item 5, which is not ranked. And we have found 4 other users in this example. I mean, these numbers 4 and item 4 to 5 items and 4 to 5 users is of course purely for an example. And users 1 through 4 have purchased not only items 1 through 4, but also item 5, the one we're trying to make a prediction about. And so what we want to do is to convert the rankings of users 1 through 4 for item 5 into a ranking for Alice. And we need to do this for all items like item 5 that Alice is not rated, but may have been rated or purchased by the users who have something in common with Alice, and that they've purchased or ranked items in common with Alice. And so we've just taken a representative set user 1 through 4. So we have to decide how to measure similarity. We have to decide how many users to make, which is typically nearest neighbor and a relatively small number, 10 to 100. And then we need, given all of this, we actually need to make a prediction for this query mark here. But the first thing to do is to find out which users are similar to Alice, because some users will be pretty different from Alice, like user 4 is pretty different from Alice, because user 4 dislikes item 1, which Alice loves, and user 4 is not very keen on item 4, which Alice loves. So clearly user 4 is different from Alice, and we actually won't want to use user 4. And so we want to try to rule out user 4 by a similarity measure, which is small for user 4. And we want to find other users which are similar to Alice and use their prediction to decide on Alice's prediction for item 5. So we use the so-called Pearson correlation. I'm not a great expert on which of the different ways might be best. This is obviously seems a pretty reasonable one. You take, if you have two users, A and B, you want to find their similarity. A and B are users now, so A might be Alice and B might be user 1. Then you take all the items which they have in common, which are here item 1 through item 4. You look at the rating of A minus the mean rating of A, the rating of B minus the mean rating of B, and you you normalize by the square root of the sum of the ratings for A and B. It looks like a scalar product divided by a norm, and that's why that's sort of intuitive. It's like the cosine of the angle between vectors. It's a slightly peculiar vector because you only sum over the components of the vector where RAB and RBP are both defined. That's why it's that's why I told you these are funny vector spaces, because you do not sum over all components, and you just sum over some of the components here, the ones where the users A and user B are both rated the same item. So when you do that, you will find that user 1 is pretty similar to Alice, 0.85. User 2 is not very similar, 0. User 3 is pretty similar to Alice, and user 4 is sort of the opposite of Alice, totally different personality. So obviously in our predictions, we'll probably not want to use user 2 and user 4, but we want to find a whole bunch of users whose similarity is high and use those in some sort of weighted fashion. So if you look at the following formula, it'll sum over users. Implicitly in that sum is only sum over interesting users, because there's no point in summing over users who are really very dissimilar to Alice.